Good catch. Any questions? So what we had gotten to last time was, this is as far as we derived things, and I want to go a little bit further with derivations, although I really want to stop this detailed analysis of Dirac matrices and Dirac fields by the end of class today, so that we can start scattering theory and Feynman diagrams and so forth on Thursday. So the rest of it is, so these are the zero momentum spinors, and what we had basically derived was this, and I've written up the notes further, so you can okay, there's a minus sign here. Okay, so that's what we had. We'd gotten that far, and then the question is, how do you put constraints on D plus and minus and C plus and minus? And the idea is that, first of all, under parity, you expect that A of P of S should go into some phase associated with particle A. We have a complex conjugation because the phase is really associated with the particle, which is formed by the creation operator. And this should be A of minus P and S. And similarly, B dagger of P and S. This is the antiparticle. This should be simply eta sub B, B dagger of minus P and S. So Weinberg uses A sub C for P, but I think it's a little bit clearer to do this. And so then, under parity, we have psi L plus positive frequency turns into a sum over S dQp integral over this 2 pi to the 3/2, which seems to me to be something that we really shouldn't have to carry around all the time. But anyway, e to the I px, and then this is eta sub A star A of minus P and S. And so now if we let P go to minus P, we get a minus P here. We get a minus P with the space components here, but we can flip that to the minus X component there. And so what we have is some S dQp 2 pi to the 3/2 UL minus P and S e to the I P, and now parity X, maybe we've just flipped the space part. A to A star A of P and S. And similarly for the negative frequency part with the antiparticles, you get the same thing, but instead of A to A star, you have A to B. And so what you get then is sum on S integral dQp 2 pi 3/2 V sub L minus P and S e to the minus I P dot parity flipped A to B, B dagger. Wow, there's a huge typo. I didn't bring a pen. Can I just use you? Thanks. B dagger of P and S. And so there are some relations that are relevant at this point. Namely, we saw that beta, gamma A dagger beta. Remember, beta is just 0, 1, 1, 0. So this basically flips the upper two components and the lower two components. So in other words, beta on something that we could call left, right, let's just make them two component spinors. So it just flips it like that. That's why beta is parity. Anyway, this turns into minus gamma A. And we also saw that beta on JAB, dagger beta was JAB. Remember that JAB, if I remember correctly, it's the minus I over 4 commutator gamma A with gamma B. Let me just flip back and check that. I see here. It's funny, right? Yeah, I guess it's much earlier. Yeah, it's equation 155. Anyway, that's correct. Okay, so because of this, we also have the beta D of L. So D of L, of course, is D of L with a dagger beta is going to be D of L inverse. Now, what's this D of L? Well, the D of L is going to be something made from the J's, because these are the generators of Lorentz transformations. And so we see that if we do a dagger and we put in the betas, then the effect on the J's is nothing at all. But on the other hand, the complex conjugation flips the sign of the I. In other words, what we have here is D of L is some e to the I omega AB JAB. And the omegas are real. The J's remain invariant under this, but the I flips, and so you get an inverse. And in particular, since J0I dagger is minus J0I, oh, there's another typo. I don't know what I'm doing. So in fact, one could write this. Oh, well, wait a minute. What we have is beta J0I. Beta is J0I dagger, which is minus J0I. So those are the relations that I should have. And so now we remember that the spinors, U of P and S, is square root of M over P0, D of L on U of 0 and S, and also V of P and S, square root of M over P0, D of L and it's L of P, V of 0 in S. And can I use this just a second? You guys are very smart to use pencils. The reason I've been latexing the notes is that I've been using pens lately. And if you try to derive the various Weinberg equations and use ink, unless you're very careful, you wind up using a lot of paper and a lot of ink. Okay, so these are our equations, and so if we remember how things transform under boosts, what we have here is U of minus P and S, that's square root of M then in P0, D of L of minus P, U 0 in S. And so this is square root of M over P0, D inverse of L of P, U of 0 and S. And then this is square root of M over P0, beta, D of L of P, beta U of 0 in S. And similarly, V of minus P and S. Let me just skip a line here. It's M over P0 then, beta D of L of P, beta V of 0 in S. And so now we can come back and identify what these U's and V's are. And I think we're going to have to go way over here. What we find then under parity is psi plus of x, P inverse, is a sum on S integral then dqp to pi to the 3/2, which I'm really getting tired of. Square root of M over P0, beta D of L of P, beta U of 0 in S, e to the I, P dot P of X, A to A star, A to P and S, and similarly to psi minus of x, we have everything is the same except we have B of 0 in S, A to B, and B dagger of P and S. And so what we want is that this should be just proportional to psi plus times omega phase, and this should be proportional to psi minus maybe a phase. And so in particular what we need is we need that beta on U of 0 and S, that's this part, should be proportional to U of 0 and S. So it should be some b sub U, U of 0 and S, and beta V of 0 and S should be some b sub V, V of 0 and S. And if we do that, then this thing turns into, then we get a B sub U out in front, a B sub V out in front. This becomes beta this becomes just U of 0 and S. D turns it into U of P and S when the square root goes away, and we have all together a beta out in front. And then what we get is P psi plus of X, P inverse, is B sub U beta eta sub A star psi plus of T and minus X, and P psi minus of X, P inverse, is then B sub V beta A to B psi minus of T and minus X. Okay, well, we also know that P squared is equal to 1, and so so if we did this thing twice, we would we'd learn that BU squared and BV squared are just signs, plus or minus 1. And what this tells us then, with beta U being BU U, you see beta is like this. And so what is U of 0S? Well, it was C plus but this thing is C minus 0. So what this is telling us is that C minus has to be B sub U, C plus, and a similar equation, this equation tells us that D minus has to be B sub V, D plus. And once we've done that, then we have our spinors as U0 1/2 is 1 over root 2, 1 0 BU0, U of 0 minus 1/2 is 1 over root 2, 0 1 0 BU, and
where did the BU and BV come from? What were they again? BU and BV? How do we know that
they first came in over here. Over here. You see, under parity, this turns the field into this. Mm-hmm. And we want the field to turn into something that will commute an anti-commute at space-like separations with itself. In other words, we want it to be essentially proportional to psi plus or psi minus.
So why?
So and it will be if beta U of 0S is proportional to U of 0S, because then you can replace this beta, which is a 4x4 matrix, with just a number. When you do that, the D acts on the U and turns it into U of P and S, and then the beta comes out front.
Sure.
And so you get, in other words, we want these relations.
Okay. So there's, sure. And then it's not like we already maybe had some constraints on what C plus and C minus are that would give us something like, oh, if we were to swap C plus with C minus, because that's all that this matrix does, right? It takes the top two entries and the bottom two entries and flips them.
Right.
Right. So is there some relation amongst C plus and C minus that we have?
Well, that's what we're getting. You see, over there it was arbitrary.
Yeah.
Here we're finding that D minus is related to D plus, that C minus is related to C plus in this way, and then V of 0.5 is 1 over root 2, 0, 1, 0 BV, and V of 0 minus 1/2 is minus 1 over root 2, 1, 0, BV0. And we're going to learn more about BU and BV in a minute. Namely, we're going to assume, first of all, that the annihilation and creation operators satisfy either commutation or anti-commutation relations like that, and the field and its, let's see, I haven't written them down recently, so I'll write them down here. Psi plus then of x is this sum over s integral dqp 2 pi to the 3/2 u of p and s is the I p dot x, a of p and s, and the sine minus of x is sum dqp 2 pi to the 3/2 v of p and s e to the minus I of px e dagger of p and s. And so now what we're going to do is we're going to do for spin 1/2 what we did for spin 0 and spin 1, namely we're going to require that the fields commute or anti-commute with themselves and with their adjoints at space-like separations. And so we're going to form this, well, I skipped a line, hold on. So we're going to say that psi of x is some kappa psi plus of x plus lambda psi minus of x. And then we're going to require that psi of x with psi dagger of y, either the commutator or the anti-commutator should vanish for space-like separations, x minus y squared greater than 0. And this, of course, is going to be kappa psi plus of x plus lambda psi minus of x, and then kappa bar psi plus dagger of y plus lambda bar psi minus dagger of y. And we want this then to vanish. And if we now substitute these formulas and use these commutation or anti-commutation relations, what we get is that this is going to be an integral dqp over 2 pi cubed now, and it's going to be a sum over spin because you have two sums over spins, but you have a Kronecker delta, you have two integrations over momenta, but you have a delta cubed with momenta. And so what you have then is kappa squared U L of P and S, U L prime complex conjugate of P and S, e to the I P dot x minus y, and then minus or plus lambda squared, VL of P and S, VL star of P and S, e to the minus I P, x minus y. And then we're going to rebaptize this. We're going to call this N L L prime of P and S, and we're going to call this M L L prime of P and S, and in which we retain the sum over P, over S and P. No, not over P, sum over S. And so this is, I made a mistake here, it's not N of P and S, it's, we're summing over the spins. So in particular, maybe I should just write that explicitly then. N L L prime of P is the sum over spin, so this is called a spin sum. UL of P and S, U complex conjugate L prime of P and S. So this is basically an outer product of these vectors. In other words, N is a sum, so to speak, U looking like that. And similarly for M. So M is the same thing. M L L prime of P is sum S, but now it's VL of P and S, V star L prime of P and S, summed over S. Okay. So let's look at N of 0. And so for N of 0, we take these vectors right here. Just 1 over root 2 is 1, 0, BU 0. And so what we get is a half 1, 0, BU 0 times 1, 0, BU 0 plus a half, and the other one is 0, 1, 0, BU, 0, 1, 0, BU. So multiplying those out and adding them, what we get is, the first one is a half 1, 0, BU 0, 0, 0, 0, 0, BU 0, 1, 0, 0, 0, 0, 0, plus a half 0, 0, 0, 0, 0, 1, 0, BU, 0, 0, 0, 0, 0, BU, 0, 1. And if we put these together, what we see is that this is a half 1, 1, 0, 0, BU 0, 0, BU, BU 0, 0, BU, let me put the 1 here, and then 1, 0, 0, 1. And now you can recognize this as a half 1 plus BU times beta.
What?
Okay, if this is puzzling, then it's a good thing that I did it in detail. Say it again?
these matrices that you're writing out are the NLL prime and the MLL prime. But why are you adding them together? Or,
Well, the
because you're going for
L
the
prime
different S values.
matrix element
Yeah.
of the 4x4
Yeah.
matrix N is the sum over S of this thing. Now if we go to P equals 0,
Mhm.
we have, well, there's an equal sign here.
Yeah.
We have a half spin up, the outer product of spin up with itself plus the outer product of spin down with itself. And outer products are like this. This is something I emphasized in 466, I think.
Yeah.
Outer products. It's something that math departments tend to ignore because I guess they never like Dirac.
How is this going to help you evaluate this integral? Because you're still going to, instead you're just going to have some Lorentz boost in there. I feel like we're not really getting around the problem by...
It'll all come out in the wash.
Okay.
Let me see how we're doing on time. I think because of the time constraint, I'm just going to tell you, you're not going to be surprised if I say that M is then 1 plus BB times beta over 2. Is that okay, or do you want me to do it?
I think it seems reasonable.
It's in the notes, and I latex the notes, and latex the typos also, and so everything's clear. All right, so what are the finite momentum ones? Well, N of P is, of course, a sum on S of outer products, or if I do LL prime, it's UL of P and S, U star L prime of P and S. But this, of course, is the M over P0. You remember the formula for, it's up there. Maybe if you flip the camera around 180 degrees, in the corner there is the formula. Oh, those are unfortunately for minus P. All right, let me just bring the thing around this way again, and I'll just write them again. Recall that U of P and S, the square root of M over P0, G of L of P, U of 0 in S, and the same thing for P. So that's how we get from the 0 spinners to the finite momentum spinners. So we get 2 factors of square root of M over P0, and then we have D of L of P, and then we have this sum over S, UL, or let us, I think we're going to write everything as a matrix now. So I'm going to write this just as a matrix. And what we have here is D adjoint. Well, there's no room to fit in D adjoint. So let me just... D adjoint of L of P. And so this is M. Remember, this is a half 1 plus B0 beta, so this is M over 2P0. D of L of P, 1 plus BU beta, the adjoint of L of P. And the corresponding equation for the antiparticles is M of P, which of course is sum V of P and S and star P and S. In fact, it would be V adjoint of P and S. This would then be M over P0, D of L of P, and then this would be M of 0, the adjoint of L of P. And so this is M over 2P0, D of L of P, 1 plus BV, beta, D adjoint of L of P. Okay, this is kind of compressed, but I take it you know what I wrote, right? Okay. All right, well, there's a pseudo-unitarity condition which we wrote down earlier, namely beta, D adjoint of L, beta is D inverse of L. That was the very top left corner of the second blackboard. And this tells us that beta d dagger of L is just equal to d inverse of L beta, and wow, I've got an extra equation here. Thanks. And this then tells us that beta multiply from the left by d of L beta d adjoint of L is d inverse is just 1, so this is just beta. So we've learned something here. The 4x4 matrix that represents the Lorentz transformation that takes us, that is the standard boost to momentum P, on beta, the adjoint of that D is beta. Okay, so we're pretty much out of space. Let me go to the front then. And I guess what I'll do is pray that this blue marker holds up for a while. Well, remember that beta is I gamma 0. And also remember well, let's see, sorry, I skipped something. It's just as well, remember that, but let me go back to the pseudo-unitarity condition again. And now I'm going to write it differently. I'm going to take, here we have d of L. I'm going to multiply this equation from the left and the right by beta. Beta squared is 1. And what you get then is that d dagger of L is equal to beta d inverse of L beta, and consequently d of L, d dagger of L is d of L beta d inverse of L beta. On the other hand, we know that that since we know that the gammas form a 4-vector, so d of L, gamma A, the inverse of L is L CA gamma C. So that's the, you look skeptical.
No, I believe you.
This is technical stuff. I've only seen it in Weinberg, and most books really skip all this. But it seemed to me to be worthwhile. Anyway, realizing that this is true, what we have is d of L of P beta d inverse L of P is then I LC0 gamma C. And now if we lower this, we can raise the C and lower this C, nothing changes. If we lower a 0, we get a minus sign. So this is minus I LC0 gamma C. And now the definition of this standard Lorentz transformation is that, and that is really LA0M, because K is 0 unless B is 0. So putting all this together, we know that LC0, this thing, is equal to PC over M. And so now we have the D of L of P beta D inverse of L of P is minus I PC gamma C over M. And we also have, from here, we have D dagger is this structure times beta, and so that gives us D of L, D dagger of L is minus I PC gamma C over M times beta. So now we've got formulas for the things that occurred in the previous expressions for M and N. Namely, we had things like D dagger, and in between D and D dagger were a 1 and a beta. And so now we get our formulas for N of P. Namely, 1 over 2P0 minus I PC gamma C plus BUM beta, and M of P is 1 over 2P0 minus I PC gamma C plus BVM beta. So they're almost exactly the same except for the BU and the BV. Okay, we now put these things into So keep these two things in mind. These are called spin sums. So we're going to put these spin sums into the expression which is on that board there for the commutator or the anti-commutator of psi with psi dagger. And when we do that, we get something that's a lot simpler. But I think I should erase this board because we've got enough time, I think, so that I'm going to put another board. So, in fact, maybe I'll just erase this board since we've got the whiteboard. All right, so what do we get then for these spin sums? What we have is psi L of x, psi dagger L prime of y, commutator or anti-commutator. X and y are space height. dqp 2 pi to the cube, because we have a quadratic form here, 2p0 from the spin sums, and then we have kappa squared minus I pc gamma c plus bum L prime e to the I p x minus y, and then minus or plus lambda squared minus I pc gamma c plus bvm beta L prime times e to the minus I p x minus y. Okay, well, these p's we can write as derivatives of the exponential. And so this then is kappa squared times minus dc gamma c plus bum beta LL prime integral dqp 2 pi cubed 2p0 e to the I p x minus y minus a plus lambda squared minus dc gamma c plus bv m beta LL prime, and then this integration again, dqp 2 pi cubed 2p0, and it's e to the minus I p x minus y. Okay, well, if you remember the definition of delta plus and delta minus, you see that this is equal to kappa squared minus dc gamma c plus bum beta LL prime delta plus of x minus y, and then minus or plus lambda squared minus dc gamma c plus bvm beta L prime delta plus of y minus x. All right, now, here's the key thing. When we first encountered delta, when discussing scalar fields, we learned that if x and y are space-like, delta is an even function of its argument. And consequently, its first derivatives are odd functions of its argument. Now, I should have closed this thing. Let me see how well this is. So what we've got is that this is actually equal to kappa squared minus dc gamma c plus bum beta L prime let me see, why am I writing that? Isn't that the same thing I had before? Ah, yeah, it's an even function of its argument. And so, let me see, I think I may have screwed up just a little bit there, so we're going to have to, let me do this by hand then. Okay, so first of all, we have the part that doesn't involve derivatives. So that's going to be kappa squared bum beta. And then we're going to have minus or plus lambda squared bvm beta. All of this times delta plus of x minus y, because this is the part that doesn't involve derivatives. Then we have the part that does involve derivatives, and this is going to be kappa squared. And now because we have derivatives, we get an extra minus sign. And so this is plus or minus lambda squared times minus dc gamma c beta delta plus of x minus y. Okay, so what we see here is we have to choose the lower sign. We have to choose lower sign, which is to say, use anti-commutators. Also, we have to set kappa equal to lambda, an absolute value. But then if we've got the lower sign, we've got kappa equal to lambda, and the m and the beta, we see we've got bu plus pb equals 0. So we have to have that bu is minus bv, and we can set it equal to plus 1 just by choosing an overall phase for the field. So that gives us a final expression for the Dirac field. It's psi L of x is sum on sigma integral dqp 2 pi to the 3/2 UL of P and S PL of PNS into minus I PX, where the spinors now, we have the final form of the spinors at 0. U 0.5 is 1 over root 2, 1, 0, 1, 0. U minus a half is 1 over root 2, 0, 1, 0, 1. But for the antiparticle, 0, a half, 1 over root 2, 0, 1, 0, minus 1, and B, 0 minus a half is 1 over root 2, minus 1, 0, 1, 0. So those are the final forms for the spinors.
What about your A's and B's? In your expression for the Dirac field?
Duh!
Yeah.
You're right. So you certainly get a candy for that. Did anybody else ask a question and not get a candy? All right. Didn't you do something? I don't know. I thought you did something here. And I don't want Sam to be left out. Okay, so these are the spinors, and then the spin sums, our N of P is, we already have the spin sums written down, don't we? Well, maybe not. All right. It's minus I PC gamma C plus M. Of course, we couldn't have them yet because we didn't know what BU and BV were. 2P0 and M of P is minus I PC gamma C minus M, because BB is the opposite, beta over 2P0. Okay. All right, so I'm going to I put the cap on both ends. Okay, so let me now write down what the Dirac anti-commutator formula then is. It's psi L of X, psi dagger L prime of Y, and now it's the anti-commutator. And so this is minus BC gamma C plus M beta L prime delta plus of X minus Y. And can I just orient your thing again? And so now the parity rules actually are, I'm going to have to do it here, parity psi L plus of X, parity inverse, beta A to A star, psi plus L of T minus X, and psi L minus of X. Minus beta A to B star, no, A to B, psi minus L, T and minus X. So what we're doing is is that previously in the parity rules, right, we had a beta U and a beta V. So the beta U is 1, the beta V is -1. And that means then if psi, which is psi plus plus psi minus, is to survive a parity transformation, then A to B has to be minus A to A star. So A to B is minus A to A star. So what this means then is the intrinsic parity of a particle-antiparticle state, which would be A to A, A to B, this would be minus A to A absolute value squared, -1. So particle-antiparticle state has odd parity. And so if we have, so there are various mesons that are known to have negative parity, and pi 0, rho 0, j psi, and these can be interpreted as S wave QQ bar bound states. And altogether, that under parity, a Dirac field does this. It's eta star, beta psi of t, and minus x. So this is t and x. Now, there's a wrinkle on this that's amusing that Weinberg points out, that suppose we have a fermion that is its own antiparticle, say a Majorana neutrino. Then we have to have A to B equal to A to A. But A to B is minus A to A star. So that means that under complex conjugation you get a minus sign. So eta for a Majorana particle is plus or minus I. So for Majorana neutrinos, if the neutrinos are Majorana, we don't know. But if they are Majorana, then their parity is imaginary, which is a bit of a shock because we're used to thinking of parity as being plus or minus 1. Yes?
Yeah, what was this business of pi 0, rho 0? I kind of missed what you were saying there.
Well, the pi 0,
what is this?
pi 0 is a spin 0 meson that occurs in the pi occurs in 3 states, pi plus, pi minus, and pi 0. And the pi 0 decays into 2 gammas in around 10 to the minus 16 seconds. The 3 pi's have a mass of around 140 million electron volts. They were this was a meson that was discovered by, discovered by Yukawa, or it was the muon that was, the muon was discovered and Yukawa wrote down his equation, but his equation really applies to the pi 0 and not to
What's a
the muon.
meson?
Huh?
What's a meson?
A meson, it's a Greek word for meaning in the middle. And so a meson is something that in mass is in between leptons, which are light, and baryons, which are heavy.
Okay.
And
So is it like a conglomerate particle?
this is, the pi zero is an up quark and an anti-up quark. And down and an anti-down quark. And you have to sum over the three colors, so it's a color singular.
So what was the relation of that to?
Well, since it's...
Parity transformation?
Good question. I've lost thread of that track, actually. Right, all right, so forget about the Majorana neutrinos for a moment. Just look at the parity of a quark anti-quark state. It has to be odd. And what is known is that the parity of all these states is negative.
Okay.
That's known from their decay properties or how they are produced. And in particular, this is the clearest case because this thing is a charmed, anti-charmed quark. And these are very heavy quarks. And so when they were first discovered, people realized that because they were so heavy, they had very small orbits, and you could use a hydrogen atom type calculation because they were so close together. It's this idea of asymptotic freedom. The strong interactions are hopeless at large distances. They are strong, and one can't do the calculations analytically. Whereas at very short distances or very high energies, the strong interactions become weak and you can use perturbation theory. So the same formulas for positronium basically occurred in this J-psi system. And it was discovered at SLAC by Burton Richter and by a guy, Sam Ting, who's been at MIT for a long time. And this is really annoying. I think Burton called it, Richter called it the J, and Ting called it the psi, or vice versa. I can't remember which did what. But instead of focusing on agreeing to call it by one name, we now call it the J-psi, which is really pretty stupid. All right, we still have a little bit further to go. We have this rule, d of L of P, beta the inverse of L of P is minus I PC gamma C over M. And this has a very nice conclusion, namely that these spinors, U of P and S and V of P and S, that are I don't know. I think we're gonna just quit, and I will have to spend another 10 minutes on Dirac on Thursday. But then I promise to go to scattering theory, which will be much more interesting and much less technical. This stuff is really technical.